Excellent. Thank you very much. It's a pleasure to be here today. Originally, our engineering manager for Europe, Sylvia Polis, who I believe a few of you know, was planning on sharing this. Unfortunately, she had to go back to Italy, so I had the opportunity to come and share a little bit about some work that we've done with a customer of ours who is also using Scilab. That's an international customer. Unfortunately, we're not allowed to share the customer name, but it stems from work that we've done inside of robotics. So first, for those of you who know Sylvia, she sends her greetings and says hello. And with that, we'll give you a brief overview of what Optimus does. I work for a company called Noesis Solutions. We provide services, and we also produce a software called Optimus. And it's a process integration software, and there's an optimization side to it. And we'll talk more about it in a moment. And then we'll get into how we integrate Scilab, how we use Scilab, and then how it was used for this particular project. So very quickly, in fact, we'll jump ahead here. What Optimus essentially is, the market segment, I believe, is referred to as PID, which is Process Integration and Design Optimization. Essentially, we make a connection platform that allows multiple software packages to share data, to communicate information back and forth between the software packages. It's good from an enterprise level, because for a number of reasons that I'll explain on the next slide, but it allows users to connect internal software that they've developed. We have a number of customers that use Optimus to connect their internal software with out-of-the-box or commercial software that they also have on a common platform across different groups, and even more frequently across different regions. After all of that information is combined, after all that software is combined, we have a lot of DOE statistical methods and optimization methods that very quickly allow for parametric optimization to be applied to those pieces of software that have been connected together. So, and then finally, there's a robust design aspect to it as well. The response surface models essentially we'll talk a little bit more about this, but it allows the users to then create meta models or surrogate models. So most of the time, the simulations that our customers are doing are running from anywhere between 2 minutes and about 20 hours to solve. And so it really doesn't make sense to do a classical or standard design of experiments, or even more so an optimization, a robust optimization. So these surrogate models are extremely important. What we found with when combining with Scilab, we were able to integrate actually with AXCOS. Most of what we'll talk about today is AXCOS, or was done in AXCOS. We were able to take that simulation data and create these surrogate models based on the responses that we got from that simulation. Optimus is a completely open platform, so we allow ourselves to be connected to basically any other software that can be driven from a command line. And in addition to that, I guess there's in addition to that, you can incorporate your own optimization algorithms, your own design of experiment algorithms into the software. We have a very simple XML format that allows us to integrate or to communicate, I guess, with external software. And so when we sat down to actually begin integrating with Scilab, we were able to pull this Scilab package inside of Optimus within about realistically within about 2 days worth of development time, and that was with engineers developing and not developers developing. So we probably gave ourselves an extra day on that. But it makes it possible then to apply. If, for instance, one of our larger customers, Pratt & Whitney in the United States, they have a mathematics group that's developing very advanced optimization algorithms that are proprietary to the group. Those are developed in a variety of different software packages that include Python, that include MATLAB, that include a few others, and they're able to immediately apply or bring those into this framework. And so without having to do almost any interface, physical interface, they can, a methods group in a different part of the building can apply the optimization routines from the mathematics group to what they're doing, to their CFD work. We're starting to see interest where these groups are wanting to move away from the traditional systems modeling tools and to use Scilab, to use these types of tools. In addition to all of that, we have a full API. So the entire process of Optimus can be driven from Python. So all of the functionality that I'll show today, the workflows that we set up today, can be created from inside of Python. What that means, in case everything else I've talked about for the customer isn't good enough, they can develop like an Excel front end that can drive all of this. So that's essentially the end of the sales pitch, I promise. So we've got a number of customers that are using, as I mentioned, a variety of tools. Scilab is one that we're extremely interested in. We see most of the interest is coming from Europe that we see right now. We have customers all over the world. We've got about 2,000 users, and there's quite a bit of interest in Scilab here in France. And so it's becoming more and more important for us as a company, as a software, to interface with Scilab. This is one example workflow. We'll see a few more of these in a moment, but this is just to point out the complexity of these workflows. Here we have, I think, technically 6 different software packages interfacing with each other. So we're transferring data from a CAD package into a CFD package, Numeka, bringing responses from that into the FEA package of ANSYS, and then doing some post-processing and some finite element analysis. Okay, so now let's talk about what we've actually done with Scilab. So the first thing that I should bring up, and maybe I should have put this first, this is a wonderful comic from XKCD. I don't know if any of you are familiar with that. We start talking about automation, and this is exactly what I say up on the top, and this is what most people realize if they've ever spent any time automating. So I'm going to come out and say, hey, listen, if you invest a little bit of time up front, your life is going to be easier. A lot of the time what happens, you spend a little bit of time up front writing this fancy little Python script that connects everything together, and then before you know it, you're spending all of your time debugging that script instead of doing the work that you initially wanted to do. And of course, if you know XKCD, they have these funny little mouse over quips. This is essentially saying that you shouldn't try to automate things. But at the same time, they have another wonderful comic that impresses upon you the importance of automating things. This is a very good table, and it's much more useful, I think, than the first comic that I showed. But this essentially is an ROI table that tells you, that compares how often you're doing something to how much time you'll shave off if you do that automation task. And when you compare those, it gives you an idea of how much time that you can spend doing something. So, for instance, if you find yourself doing something once a month that maybe takes you 10 minutes to do, it doesn't make any sense at all to spend any time automating it. You hardly ever do it. It's very low value added. On the flip side, if you're doing something, say, like tuning a PID controller that you do once a week for your controls group, and it takes you an hour and a half every time you want to tune those, that's something that you should be interested in automating. And that's exactly what we've done here. In fact, on my back of the envelope calculation, you should be able to devote about 10 days worth of automation time and still be okay. What we're going to show today is that we were actually able to automate this tuning process in about 5 minutes because of the flexibility of Scilab. So we're in the clear in terms of return on investment. Now here's how we integrate with Scilab inside of Optimus. The dialog box that we use here basically is going to be the same. It's a very generic dialog box. If you're familiar with the software, with Optimus, you see this dialog box basically every time you open the software. Essentially, we have these user customizable interfaces, as we refer to them. They're driven by a text-based XML script that essentially points to the libraries inside of Scilab or some internally developed code that you may have done or that we may have put together. After this is set up, you've got this drag and drop. Oh wait, I've got an image. An image of the XML script, and you can see it's very straightforward. After you've set this up, you have drag and drop functionality inside of the software. And that's exactly what we've done, and that's exactly what we're showing today. This is the workflow. This was the final workflow that we delivered to the customer. It went through a few iterations. But essentially, the user specifies the variables for the PID, feeds that into the SCE script, which calls the AXCOS project. The simulation is run. I think I noticed, I was just looking through this before, I say somewhere that the AXCOS simulation took 30 seconds. It was probably closer to a minute or a minute and a half. But anyway, you wait that time, and when it's done, Optimus automatically extracts the results. Is this something that you can do without Optimus? Absolutely. Is this something that you can write a Scilab script to do on your own? Absolutely. There's no question about that. The challenge comes when you then want to distribute this, or when you want a variety of different people to be able to use this. And this is why our customer came to us and said, listen, we're about to spend a month creating this automation platform in order to do this one simple project. Can you guys handle it for us and give us a workflow back? And that's exactly what we did, and we were able to do it seriously in about 10 minutes worth of time. So the project itself is a robotic arm, as you can see here. This isn't the actual product, but it's not too far off. Let's talk about what we do. Obviously, we know what a robotic arm is. We know what it does. Each of the joints have basically one of two movements. They can either move linearly or angularly, so they can rotate or they can extend, just like your arm. When you're driving these arms, you give it a command. You say to the arm, this is where I want you to go. The servo motors then do their best to begin moving, feed some data back and say, hey, this is where I'm at this millisecond, this is where I'm at this millisecond. And of course, there's going to be, just like maybe with your arm, sometimes there's a little bit of overshoot, and so you have to bring it back a little bit, and you end up in this process until you end up exactly where you need to be. Of course, with our brains, we do it instantaneously. It's not a problem. In the mechatronics world, it takes a few hundred milliseconds to do. The PID loops that control these are extremely important. Basically, the control system for this particular robot has a PID loop for each individual servo motor. Those are basically tuned at production time. There are situations where you need to tune these PID loops in real time, and so you're always updating and you're always tuning these PID loops, and that actually opens up a wide variety of applications for optimization. And when we talk about optimization here, there's probably a few different feelings about optimization. When I say optimization to someone, if you're an engineer like I am, you hear optimization and you think, hey, I'm going to run I'm going to try 4 different things and pick the best one. When today, right now, for the purpose of this presentation, when I say optimization, what I mean is actually a thorough analytical analysis of a design space where we're running tens and hundreds of experiments to determine the gradients that we need to be to find a theoretical optimum. So it's more than just this kind of guess and check approach, or plug and chug approach, I guess. The PID control, I assume most of us know what that is. Basically, it's a proportional integral device. It takes information, basically calculates the difference between where you want to be, where you are, and attempts to minimize that difference. And if you'll notice, I don't think I have it here, but basically you have kind of a transitional curve until it reaches some steady state at some time in the future. So that's what we're optimizing. We're going to be changing the values for each of these components. The proportional value typically starts at usually around 1,000 if it's set up right. Integral and derivative sides are usually at about 0. I really should have put a PID response curve in here. I apologize. So the challenge, I think we've already talked about. The time to tune these PIDs, really, it's a custom process for each PID that you encounter. It becomes even more complex when you realize that for that little robot we had that we showed earlier, there were 6 different PID loops. For the one that we're working on here, there's 3 different PID loops that we have to tune. Basically, anytime the design changes, the PID loop needs to be retuned, or the PID needs to be retuned. So where did we start? We found this great toolkit or toolbox, I guess, from this professor in Thailand that refers to himself as the Scilab Ninja. I didn't have any previous interaction with him, but going through this guy's webpage, it's really fantastic stuff. He teaches controls in Singapore, and he's put together this fantastic robotics toolkit, this RTSX. He talks about on his webpage why he did that. I know there is a robotics toolkit that's included with Scilab, but there are also a few other versions out there. He says beta version, but we didn't, in the time that we've put into this toolbox, we haven't had any problems with it. So that's the inside of Scilab, what we're going to be using. When we talk about evolutionary optimization, the concept behind evolutionary optimization is essentially starting off with your entire design space, throw or sample, use maybe 10, 50, or 100 experiments for a population. Take the response from each of those, determine which your best performing experiment was, reduce your design space and move to that location. Basically do this in an iterative process until you've reached some sort of termination criteria. All right, here's the AXCOS project. As you can see, this particular one is a linear joint, I believe. It's not particularly complex. The part that we needed, that we were interested in, was the disturbance factor that we could turn on here. Of course, it's receiving some data from the workspace, transmitting the data back to the workspace. The information that it's sending back is simply the error or the integral of the error, so that we know how close that we're getting. The Scilab script then is extremely easy. Extremely straightforward. You can see how we've set it up here. Basically, we specify the variables that we're interested in, so the P, the I, and the D values, and then Optimus on our side automatically picks those up and can begin driving the workflow. On the output, here we go. We point out the output down here. We're both writing some files out so that we can do some post-processing in Excel after the fact. And then we also, Optimus has the ability to read the information directly from the memory. So it decreases the amount of time that the simulation takes. We looked at this interface before. You guys know what that looks like, and of course we looked at the workflow before as well. The comparison between the target curve and the objective curve, and the baseline curve are calculated actually inside of Scilab. So all we do is export the absolute difference curve, integrate that inside of Optimus, and that's our error integral down at the bottom, which becomes our objective. And I think this is a video of setting this up, but it doesn't look like it's going to run. So if it was running, you would essentially see, you can tell this was from an early version of the workflow. We're only looking at 2 different curves, but basically the process here is just showing how we launch the run, and then the data that's coming back, the response that's coming back from Scilab. It's not transparent. So in our case, Scilab was launching a few curves just so we could monitor the process with each experiment, but it was running a number of, in fact, in this particular case, we did a design of experiments that ran 100 experiments completely unattended. So with about 5 minutes worth of time to set up the workflow and 3 button clicks in order to launch the design of experiment, we come back an hour later and we have all 100 runs done. Now, we said that just running and picking the best one wasn't an optimization. This is the strategy that we use. We do the design of experiments first, then we create a surrogate model or a response surface model based off of that DOE. We do the global optimization, which requires many hundred experiments, but we run that on the response surface model, so it's done instantaneously. We then, after we take that result, we run a local optimization and arrive at our goal. And I think we're running a little short on time here, so we'll burn through this quickly. This is the results of the design of experiments. Here you can see a few of the response curves, or the difference curves, I guess. The red was an extremely high PID value. The blue, actually the light blue, which is back here, proved to be our best PID values. Here are what the response surfaces look like. Again, this is a mathematical model, so we run on those and it runs extremely fast. If you wonder what a response surface is, come talk to me afterwards. The evolutionary optimization strategy, then, the goal of this paper, wow, we're out of time and I'm finally getting to the purpose of the paper. We wanted to find which was the best strategy. What we found is that what's referred to as a simulated annealing strategy got us to a very good answer, in fact, almost the best answer in the least amount of experiments. So that's what we were interested in. There you can see our simulated annealing. The resource impact is what ended up being the most impressive here to us. It took about, more or less, about 180, we saved 180 minutes, so 180 engineering minutes using this Optimus approach versus using a traditional approach. So looking back at our table here, we had 10 days to do it, and we developed this workflow in about 10 minutes. So it was fantastic for us. This is all salesy stuff, so we'll skip that and open the floor up to questions. I apologize for speeding up there at the end, but if you have any questions about this that you want to get in a little more detail, I'll be here all day. So.